new app for streaming. You know, it's easy to stream games, but streaming from applications for live coding, papers, it's not as easy as you'd expect. Or maybe I'm just kind of ashamed that I'm not as good at this online production stuff as I'd like to be. But let me try and share my screen here. So today I'm going to go through a tutorial that one of my students put together on counterfactual reasoning with normalizing flows. Like if you saw this, I knew and told you that this time I would do, you might have heard me say I was going to do a little bit of a a tutorial on Turing.jl, and I think I'll do that later. This came up recently from some very talented students that I've had the pleasure of teaching, and I haven't had a chance to actually go through it yet. So I want to do that. How do I share a screen on this thing? Tutorials. It's one of these awful I have too many apps open. Okay. I just share my whole screen. Hopefully I don't get any weird messages. Desk, Jupyter Notebook. Oh man. I don't even know how I have these many apps open. It doesn't look like I have this many. Tutorials. All right, let's just share the screen, I guess. I'm probably eating up so much bandwidth just having all these things open. I don't even know. I didn't realize I had the Firefox open in multiple windows. All right, let's just share the whole screen. How does that look? Okay. I do not know what that looks like to you. Probably, oh, it's like one of those split screen things. Let me see if I can't. Maybe this is probably better. Let me make sure that looks okay. Give me a second here to confirm. Does it show me what I'm? Does it show me much what I'm even sharing? Am I sharing the right screen? Oh man, the quality is so bad. Yeah, I'm using this restream service. I wish they had an app. This is an online. According to this thing, I am not sharing. What is it? Oh, I have to press this, turn that on. What does that do? What's this Christmas background? Oh God, that's hideous. All right, we'll have to do with that. Oh man, I am not a fan. Is my sound okay? Ugh, hideous. All right, well, let's go ahead and get started then. All right, so we have this. And so again, this is a. So if you are, this is wrong. What is this? I want counterfactual. Should have gotten merged. So what this donuts thing, isn't it? So we're looking for a tutorial on how to here it is. Reason with do counterfactual reasoning with normalizing flows. So normalizing flows are a special kind of approach to deep generative modeling that allow you to they make it so that the neural network the forward generation of the model is invertible, so you can you can reason, given some say given an image, you can work back to the values of the latent variables that generated that image, and that's important. And could not find a kernel. Let's try. What does that even mean? It's important so that you can do the Pearl's counterfactual reasoning algorithm, which has 3 steps. Abduction, which is that backwards inference step, and then you do some kind of action, and then you forward simulate on the let's try that Vem. I think that's where I installed PieTorch. Man, everything's super slow now. Okay, set kernel. Hopefully this loads. All right, whatever that's doing. All right, so I guess I'm gonna suffer for some huge lag. This is not gonna be tenable. All right, let me close some other windows. Maybe that's gonna. All right. Oh. Okay, so read through this here. We got. I'm going to start with introducing normalizing flows. Talk about the twin-world counterfactual inference algorithm. Right. So this is the algorithm I just mentioned, and so this is an algorithm for reasoning counterfactually. So you observe something, like say, do an action, get some kind of results, and then given that you did that action result, you try to imagine what would have happened had you done what the result would have been if you had done a different action. And there's and Perl has an algorithm for doing this that's universal, called a twin-world counterfactual algorithm. It has 3 steps: abduction, action, and inference. And so abduction just means that we're going to, given the action, given the action and the result, we kind of condition on what are called exogenous variables in a structural causal model. You could think of them as a kind of latent variable. And we infer what those variables are, and then so that kind of gives us the initial conditions that led to those outcomes. Then we apply this action that is the alternate action that would have been that you would have had, could have, should have statement, and then you forward simulate in that last inference step to see what the new result might be. So. And so let's see here. Normalizing flow is a kind of neural machine that transports some simple but often high-dimensional noise distribution into a more complex, sometimes high-dimensional distribution. Often the base noise distribution is a Gaussian. We apply this sequence of neural networks in such a way that we obtain a valid probability distribution and can invert the composition of the neural networks, right? So we're interested in being able to reason backwards on a neural network. We also we can tractably compute the determinant of the normalizing flows inverse Jacobian with respect to base distribution value. So this is just a little bit of probability theory for exactly how we reason backwards on a neural network. In this case, a neural network that's transforming so you sample from a Gaussian and then you transform it through this network. You transform that Gaussian through this network, and so you want to save some information about that transformation In probability theory, that's the that information is stored in that Jacobian matrix, and then then the inverse matrix allows you to go from the output of the neural net back to the input Gaussian. And so with invertibility and tractable computation, we can compute the density of the output exactly using change of variables formula from vector calculus, right? We also exactly recover the value of the base noise distribution sample that generated the flow's output sample. By way of example, suppose we are interested in modeling a set of pixels using a normalizing flow that takes samples from a high dimensional isotropic Gaussian as input. Each components of the normalizing flow, shut up. Turn this off, sorry. Each component of the normalizing flows move the Gaussian noise in such a way that the noise values don't bump into each other. It's a technical term, but move toward the desired pixel distribution. We recover. What does that mean? All right, so we got some components. What components are we talking about? Oh my God, it's not letting me highlight. I have a strong suspicion that this is gonna. Okay. Mm-hmm. One second here. Let me just optimize my settings a bit here. Be much better as an app, but whatever, we'll work with it. And I really hate this Christmas theme. I got to figure out how to change that. Okay, so components. Normalizing flow that takes samples from high dimensional isotropic Gaussian as input. Each component. So components of what? Each component of the normalizing flows moves the Gaussian noise. All right, so normalizing flow has several components. It's moving, kind of transforming this noise. They don't bump into each other, so there's not some kind of loss of signal by combining noises, and move towards the desired pixel distribution. We can recover the noise value that generated the image by passing. Oh, can you even see that? Let me increase size there. So, okay. I'm going to do a view here. Also, I'm plagued with technical difficulties today. Oh, there we go. And that's big enough. Guys, I'm gonna. Huh. Yeah. So I'm just a little bit more bandwidth for this operation here. All right. Oh, really? That seems to be expensive. Let me close that. All right. Normalizing flows are useful in cases where we want tractable and efficient computation of noise variables that generate desired output observations. As we will see below, this is precisely what we desire when performing counterfactual inference with structural causal models. So we're going to do this 3-step counterfactual inference algorithm. When we have a structural causal model over some set of variables that may be represented in a DAG, we may perform counterfactual inference. Counterfactual inference involves performing 3 steps: abduction, action, prediction. So abduction, so we predict the state of the world, namely the exogenous variable. So these would be the latent variables. So we say we observe some variables x1 and x2 in our system, endogenous variables in the DAG, and there's some kind of latent variable, which in SCM language is called exogenous noise, that we want to infer. Then we're going to do an intervention. See, this would be nice if factor, instead of using the word factor here, they used x1 or x2, but that's fine. Corresponding to the desired manipulation in a modified model. So what is this notation? G hat equals G. So I guess G is the model with a new, some kind of intervention. And then, not sure how I feel about this notation, but we'll just give them the benefit of the doubt here. Compute the quantity of interest based on the distribution entailed by the new counterfactual model here. Okay. This looks like Bernard Shokoff's notation, I guess, like in that book, Elements of Causal Inference, but or not, though. That's not exactly how he writes it, but we'll see. Our ability to perform these 3 steps is usually limited by our ability to do abduction of the exogenous noise variables with normalizing flows. We can exactly abduct. Abduct. I don't think I've ever seen it used, that term directly uses the word. It's just a word for inference, right? But I guess it means going inference in the reverse direction. Exactly abduct the noise variables that generate the outputs, modeled by normalizing flows by taking advantage of the invertibility of the flows. Moreover, we can perform abduction for high-dimensional outputs like rich media. Contrast this property of flows with variational autoencoders, which are not usually designed to be invertible and provide efficient inverse Jacobian calculation to require we perform approximate inference of the base noise variable. So, when I look at, let me just summarize again what we're doing. I personally think, like in causal machine learning, it's the counterfactual questions that are of that are especially of interest. I think so there's a hierarchy of causality. There's just the observed data, things that you can predict, regular machine learning. There's intervention. So I do something, change the distribution that the model might have been trained on, and still try to predict in a world where things have changed. And then there's counterfactuals, which is where I observe something in the world and then think about how things might have been different, what outcome might have, how something I've observed might have been different had some intervention been performed. And counterfactuals are interesting because they provide a way of, cognitive science tells us this is very much the way that humans reason. You make some decisions and maybe you get a bad outcome and you think, like next time, had I done things differently, I would have gotten a better outcome. You don't know that. You're using a kind of internal model of the world to imagine how things might have been different. And that imagine is a kind of generative simulation that's done by a generative model in your brain. And it's important because you're basically making a decision on information on outcomes that you haven't actually seen. They're counterfactual. And it's really important that we're able to make learning agents that can reason the same way, because we want agents that can learn how to do something without actually seeing a cause-effect outcome, but being able to imagine what from learning causality, being able to imagine what the effect might be to avoid negative steps. are suboptimal to some kind of reward function. And I think this is really interesting in terms of models, but also in terms of generative modeling, like we see with images and with videos, like deep fakes and stuff like that. A deep fake is a kind of counterfactual model, but trained specifically with respect to one task. What we want to have is to build causal generative models that, that are task agnostic, that you can define the thing that you want the model to imagine after training it with that, or rather than having it be a specific training, having the query that you want to be targeted during training. And so this is, normalizing flows are a great way to do it with images. There's actually a great paper out there. I think it's called Tractable Counterfactual Inference or Reasoning with deep normalizing flows. So this is very much based on this. Except we're using, and that paper uses Pyro, although from what I understand, the code base isn't that great. Research code. Flow of the tutorial, pun intended. So this is also using Pyro, and we're going to see if we can't get this to work. Although, we might just have to read through it since it looks like I'm having some. Okay, looks like things are back to normal. So like import donuts. All right, here's I don't know if I have everything that's listed here actually installed. So we'll see in a second. Man, why is it even, I've never seen a Jupyter notebook not load like this. No idea what's slowing things down. All right, what we got here? We need Seaborn. All right, I can do that. I can do with that. All right. So. Let's do Seaborn. Show up. Oh, that's real annoying. What else do I think I might? I have, but probably don't have, or think I might not have. Okay, Seaborn. Do I got sklearn? I'm not even sure I have sklearn. Let me go. Ah, that is. I've never seen Firefox do that. So, yeah, I was using my MacBook Air to stream. It's 3 years old. Maybe next time I'll use my MacBook Pro. I never actually had encountered an issue like speed issues like this. I guess this is why gamers buy PCs. All right, so we got C. Oh, let's just see what else I might need here. All right, loaded. Oh, nope. Sklearn. Oh, that's right. Yeah, I don't know why they would do this from the browser. It seemed to be better just to. How are we doing? Have an app that you can download. Updated my sound settings. It should be a bit better. If you can't hear me, type something in the comment box. Okay, so how are we doing? Did it run? Okay, it ran. Okay, so run that. Create a data set, donuts data set, 1,000 samples. Okay. Oof. All right, so it's running. Okay, so start training loop using our gen model. We'll use our observed data to condition the model on the data and extract a trace from the condition model. The built-in functionality of a Pyro module is used to compute the log probabilities over the trace output. So a trace is, so when you condition, so a trace is like in a probabilistic program, you execute the program once and you get a program trace. That's just one execution of the program, one set of values that your model generated, and you condition the model on data, and then you'll get a condition trace, which will have, well, so why do we want to trace from a condition? We're going to condition on data, I guess, in that first step of that abduction algorithm. The built functionality of the Pyro module is used to compute the log probabilities over the trace output. Then the log probabilities are extracted over the specified observed values. The element-wise sum is taken as the mean. Wait, let's slow it down. A Pyro module is used to compute. I don't know what a Pyro module. Pyro's. What have I done here? Is used to compute the log probabilities over the trace output. And then the log probabilities are extracted over the specified observed values. So I don't really understand these sentences. I think, a Pyro module is like what? Is that some subdirectory of Pyro? Are extracted over the specified observed variables. Okay, the element-wise sum, and then the mean is calculated. I guess maybe what are we taking sums and means of? The loss is stored as a negative of this value and is minimized for observation. The main nuance from the training step loop in normalizing flows is setting the clearing of the cache of the model's stateful flow variables at each optimization step. Okay, so that's a bunch of gibberish. Maybe I'll ask the writer to clarify a little bit for this is the first time I've seen this training loop implemented in code. See if we can understand it. So we're optimizing, I guess, over observed variables, data set, epochs, learning rate, number of samples, atom optimizer. All right, flattening stuff, losses. He gets on the data. Get the trace. Compute the log probability. So that's what he means by Pyro modules, I suppose. Then we're going to, calculate the loss as what? Okay, you have to, so this is some kind of method that calculates something. And then we're going to take that model trace. We're going to get the log probabilities. Why is it a partial? Because the variables are different. So we'll get a whole bunch of, so for each one of these variables, we'll calculate the log probability and then sum them all up, take a mean and then take the average. And then take the negative for our loss function and then try to minimize the log prob here. So, okay. So where our loss functions, we're minimizing. So, okay, clearly this is kind of maximum likelihood here. Maximum likelihood of what? The condition model. Have we specified a model? What's the model? Did it just... Where'd the model come from? Oh, it's an argument. Okay. All right, so it looks like we're taking some kind of maximum likelihood. So this over bars, what does he say over bars was? We're taking maximum likelihood. Log probabilities are extracted over specified observed values. Don't really know what that bit's all about. We're getting log probabilities. So this get log prob must be getting it from this trace for a specific value here. I don't know how you would just get them all at once. And, well, I guess that's what he's doing. You're getting them and just, getting them using the map function for each variable in this over vars and then summing them all up. I wonder why you have to do that. I wonder why you can't just... I wonder why I have to do all these steps to get the log probability from a condition model. It's been a while since I looked into the guts of Pyro, so maybe that's how it works. Let's run this code here. All right, we build a base class that inherits from Pyro module and contains several methods that will be reused across the progressively more fulsome versions of the model. Important notes on implementing of flows based on this Pyro module framework. Registering buffers is needed for the flows to train on a stable latent space. This will be training a transform distribution instead of training the distribution directly. This transform distribution is an affine transformation. All right. Okay, so registering some buffers. So using a whole bunch of kind of Pyro internals to come up with some useful functions here. So let's just run that. So this looks like boilerplate. It'd be nice to have some comments here. Oh well. See if I can make some. We'll come back to it. Tutorial on normalizing flows in Pyros, mirroring normalizing flows Pyro tutorial in the Pyro module framework. Can we skip down to the counterfactual bit? Yeah. Well, we could run through the tutorial first. So this would be regular normalizing flows. Yes. We're going to do a spline transform. So this is the flow. So it's just a spline. This doesn't look very neural networky at all. But I guess it could be any function you like, so long as you can calculate the the you can maintain all that information in the transform. So we sample from a normal distribution, we create a transformed output here. So this flow dist, which is a transform distribution that takes in this transform here. I wonder why it's a list. Can you apply a list of transforms? And then we sample a value x, and then return x in some fashion, some tuple of version of x. So we can smoke test it. All right, and okay, so that's training slowly. All right, we'll have to stop that. So, okay, once again, what I'm doing here is trying to understand, we're trying to go through this tutorial. Oh, there we go. She's kicking off now. We're trying to go through this tutorial on normalizing flows, and particularly using normalizing flows to run a Pearl's counterfactual 3-step abduction action inference algorithm, which is a way that we can get learning agents like this one to imagine alternate scenarios. In this case, these should be images, so we'll see some. I guess we haven't actually seen what the data in the image and the data looks like yet, but I'm loath with the way my system is. So if it'll visualize the model when we're done, but with the speed that my system is taking today, I'm loath to do that. I might. Looks like, we're, yeah. So what is the, so we have that training step here that's minimizing, or maximizing log likelihood over some, or log, maximizing log likelihood. Let's read on while this is working. So flow-based multivariate model. The following is an application of the multivariate distribution transforms Pyro example. So we got, all right, so that was we got one model, univariate model. We got a multivariate model here. So this, now we're taking, all right, we just have 2 dimensions. So we're still doing a spline, a coupled spline here. And then looks like we're doing basically the same setup. So this is just proof of concept. Oh, look at it. So we see some pictures. Looks like the data is this perfect circle, and the flow here, 2 concentric circles. So this is why it's called donuts. And so the flow seems to be generating at least close. Probably you can run it, if you ran it for a few more epochs, it would get better. Looking at the marginal probabilities. Okay. So I guess when we visualize this individual model, then we'll just see something that looks like a histogram. Oh, did I run? Nope. We're almost there. I guess we'll just sit here and wait it out. We're almost there. Why it pauses like that? All this makes me want to buy a Windows computer. All right, so show me the visualization. We can see this univariate distribution model captures the marginal distributions of x. Oh, there we go. Ooh, that most certainly did not work. I mean, it looks like it's getting there. It's on the borders here. It looks like it's got some more epochs to run if it's going to work. Although the marginals are fitting. So this is actually interesting kind of consequence. Like recently I've been working with Bayesian models. I work Bayesian models a lot, and you have these things in Bayesian modeling called posterior predictive checks, where you fit your model and then you simulate data from it, and then see that simulated data matches the original distribution or the empirical distribution, and that's what we're doing here. And it's actually it's easy to kind of look in one dimension and see that it fits pretty well. It fits pretty well, but then the higher order things tend to get lost because people typically assume that if it's fitting on one dimension or two dimensions, then the higher dimensions is probably doing well, but it's almost never the case. And then when you can kind of deliberately construct something like these donuts, then you get you see that you see good examples. Like if you imagine you're standing here on this x-axis looking at the donut, not seeing things from this angle, and so you see kind of going on you have a whole bunch of points on this axis, and that thins out, and then you have a whole bunch of, because there's a donut in the middle here, and then you have a whole bunch of points here, but then it also thins out because there's a hole in the middle here, and so that's why you see this lots of points thins out, 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 but then and it's kind of capturing that density from one side. It's not capturing that, so it looks like on this x2 axis, we're not really capturing the thinning of points in the middle here because we know where the hole is. But even if it were, you can still imagine that from this two-dimensional standpoint, you're still missing a little bit of nuance here because of these. It's getting kind of build-ups on these squares. But I think if you ran it more, it would probably be a little bit better. Let's see if we can't jump down to. So this is actually. Maybe there's something I'm missing here in terms of why this is working. So what is the difference between this univariate and this multivariate? So maybe I guess the point here is the multivariate must be doing a better job capturing the nuances of the donut shape. So here, if we looked at these models, what do we see is different? We got binary location, binary scale. We got a spline. So we model marginals as univariates. Here we model x1, 2. So where is the modeling of marginals then? So here, to event. Must be here. So here we use a regular spline. So it looks like it's just kind of fitting a spline. So a spline is one of those kind of polynomial curve fitting things. So it looks like we're fitting a spline. So Spline is like the 1990s version of a neural net, right? And so we're just it looks like what we're doing here is just fitting we're fitting X1 and X2 separately. While this so-called, this so-called spine coupling is modeling both X1 and X2 at the same time. And so we get some more faithful representations of the donut shape, although we seem to be deviating here for some reason, which is actually an interesting artifact. I'm wondering what's causing that. All right, so basic flow-based conditional model. The following is an application of the conditional distribution in this new Pyro module framework. Finally, we show how to model the joint distribution using the conditional factorization of the joint distribution. P of x1, P of x2 given x1. Understanding this implementation is key for using normalizing flows as mechanisms in SCMs, even if it does not necessarily yield any important performance advantage. All right, what? Understanding the implications key to using normalizing flows as mechanisms in SCMs. So we're still kind of building up to using SCMs. So given that we have, we got 12 minutes left in the session. Let's see if we can't. Oh, wow, that's much better, isn't it? So they're doing something different here. May as well understand it. So model the joint distribution using conditional factorization. Great. So we're not using splines anymore. So it looks like, I see. So our flow in this case is using a spline to model X1 and then a spline conditional on X1 to model X2. So great. So here we sample from the normal. We get the spline to model X1, the conditional spline to model X2 given X1, because we take this thing here and yeah, where does this guy show up here? How is this thing using information from X1? Yeah, that's not clear to me. Here. So X2, we sample using this object has a condition method that we condition on X1. And then return both of these. Okay. So this seems to be working much better. Oh, look at that. Surprising to me that that's working. I can't think of any logical reason why that should work better than, maybe it's just the nature of splines, but a spline that's modeling a joint versus a spline that models one and then a conditioned spline that models another. Been a while since I looked at splines though. All right, adding more complexity to conditional models. So we want to get to before diving into the full SCM, we first demonstrate how we extend our conditioning set to include more context variables. The intent of this step in the tutorial is to make clear this extension without getting bogged down in some other implementation nuances that will come with the full SCM and the methods that will implement the abduct, act, predict, counterfactual algorithm. Though we expect no performance improvement over our models because of the context variables are not varied by data point. Don't know what that means, but let's see what we. Let's see here. So we got a flow here, an affine transform, a conditional spline, sample from a noise. We got a so we got a noise dist, another noise base dist, noise flow log norm. So we get some kind of log normal noise. Not really sure why. X1, X2. So let's see here. We sample noise. We sample X1 given the noise, whatever CTX is. I'm not sure what CTX is. But it looks like it's dependent on X1. So we sample X2 given X1. All right, so you're just adding some complexity to the model to make it look more SEM-ish, but it's not doing that much better. Great. So flow-based conditional model of continuous context variables. Wow. Let's see if we can't jump down to in the time we have left. So there's a lot to sink one's teeth in here. If you were interested in working through this tutorial on yourself, it's in the causal ML repo on my GitHub account, Robert. So Robert Ness / causal ML, all one word, in the tutorials directory. So, all right. So here's our. Okay, we're messing about. Okay, so we have. This will be our SCM. So we already kind of know what the structure is now, and so we're just going to be implementing this DAG. I dare not try to actually train this. But I might have to see a visualization of the model. All right, so let's see. Yeah, I'm curious how they actually visualize this, but so it looks like we have enough ingredients here to, it looks like they haven't actually done the actual abduction, or did they? Let's see here. So we have our model. And we have a step for inferring the exogenous variables. So what do we do here? We're going to take in our data, we're going to condition the model, get the trace, then try to muck about with the trace a little bit and get some kind of, get the, that base distribution, and then get maybe use that output name base equals compose transform. Okay, so it looks like this logic here is grabbing these, we'll be inferring these n variables, which is the first step of the abduction action inference algorithm. And then right, load, and then we observation conditions. So we infer the exogenous variables, we apply so we apply the intervention to the condition model using like by conditioning. So we conditioned the original model on the updated versions of the exogenous variables. So we apply the intervention where condition here is the name of the intervention. I wouldn't call it condition though, it's confusing, but yeah, and that'll work. That looks right to me. This is great. Got a smoke test, or hopefully we'll get in. We'll see how. I'm not sure. I'd be curious to see what visualizations that came up here. Particularly informative, but let's run this and wrap up. Hopefully, there's not something here that I would have had to define early above. If we're lucky, it's all self-contained. Come on, it's just a function. It's just and yeah, so there's an error. That's why it's doing that. Oh no, it's running. Okay, cool. We already have a sneak peek of what the output's going to look like. So yeah, all right. Well, at least it's fitting. So it would be really cool to think about what kind of images we can generate. But these, generating on these counterfactual reasoning on these donuts isn't particularly meaningful. Okay, so working with this group of students to actually generate some meaningful counterfactuals. Like, so there's this. Google has this tune faces. All right, so I should write Google. Anyway, there's a whole I don't know what it is, but like Google has some data set of faces that you can use to train things like GANs and stuff for realistic face images, and it's going to be a simpler problem, although there might be some training issues with working with cartoons. But yeah, you can ask, what would this face look like if it had a mustache, or if the skin tone was darker and stuff like that. And so, yeah, we're excited about working on that data set. But hopefully, and so next time I'm going to be working with this Turing JL tutorial. There's a whole bunch of really cool things happening in Julia when it comes to probabilistic programming and modeling, and Python and some other ones too. So I think and there's a nice causal library called Omega. There's one called there's a probabilistic programming language called Gen, which has something called Genify. Paper just came out recently. It's been submitted to LAFI, which is learning abstractions. I don't know what that means, but something about languages. But like, it takes a simulation program that you can write in any kind of simulation that you can write in Julia and converts it into a probabilistic model. So I'm excited about going through those spaces of models, and we'll have a lot that we can work with there. So awesome. If you're watching the recording of this, thank you. If you're tuning in, thank you. And hopefully I'll chat with you next time.